Study Unit 7, Lecture 5. So this lecture will focus on resonant voltage source inverters. Shown in this diagram is a series resonant voltage source converter. It's got a series LCR network, got two freewheeling diodes, and two switches, T1 and T4. The reason they're labeled T1 and T4 is because this is actually only half of a full bridge, which would have a T2 and T3 in parallel with these. To simplify the analysis, however, only a single leg is first considered. So this circuit makes use of the series resonant network at the output, and this network is being driven by the two switches T1 and T4. The idea behind this circuit is that for every half cycle, so with either T1 or T4 on, energy will be put into the resonant circuit. The circuit will resonate and thus provide enough energy during the second part, or the second half cycle. The Q of this network, or the quality factor network, determines how much or how effectively voltage is transferred from the source to the load. So in this diagram over here, the higher the Q, the more effectively energy is transferred to the load at the resonant frequency. If the Q is lower, then energy is dissipated as reactive energy inside the reactive components. It is at this point that the load becomes either capacitive or inductive. So how this circuit operates depends on the timing of the two switches which drive the switching in the circuit. The two types of operation are called either a lagging operation or lagging mode and a leading mode. The lagging mode is induced when the switching frequency present on the switches T1 and T4 is higher than the resonant frequency. From this voltage transfer function over here, it can be seen that if the switching frequency is higher than the resonant frequency, then the load has an inductive behavior. Because this inductive characteristic starts to dominate, the load current will start to lag behind the load voltage. So shown here is the output voltage, which has an AC characteristic, and shown here by the red dashed line is the output current when the load is behaving as an inductive load, and it can be seen that it lags behind the AC voltage at the output. In this configuration here, switch T1 will be conducting when diode D1 is conducting. So at the start of the cycle, both T1 and D1 will be conducting. As time progresses, the amount of current which D1 is conducting will start to decline and more current will flow through T1. Eventually the current through D1 will be zero and all the output current will be flowing through T1 and the oscillation will be through switch T1. During this whole process, this capacitor over here will also be charged up. At some point the voltage across the capacitor will be at a maximum and then the oscillation will reverse direction. In other words, when the capacitor is fully charged, then diode D4 will be forward biased and current will be able to flow through D4 and thus turn on T4. This conduction through D4 and then T4 and eventually only T4 characterizes the second part of the half cycle conduction. The lagging behavior by the inductive load results in a discontinuous or hard switch off of the currents through either T1 or T4, and this is where the oscillating current will not gradually come to zero but will instead be drastically returned to zero. This results in a almost discontinuous current behavior through switches T1 and T4. For the leading case, the load behaves as a capacitive load because the switching frequency is now less than the desired resonant frequency. This causes the output current to have a leading behavior where the AC characteristic of the output current leads in front of the AC output voltage. In this case, switch T1 will only conduct when diode D1 is not conducting at all. And same for switch T4. Switch T4 will only conduct when diode D4 is not conducting. For the analysis of this single leg inverter, it is assumed that the switching frequency of the inverter is approximately equal to the resonant frequency of the network. So with this assumption and assuming that the initial current through the network is zero, then the current through the load is given by 1 over 1 minus e to the minus alpha t over omega multiplied by the source voltage over omega L multiplied by e to the minus alpha t multiplied by sine omega t. This equation is valid for both parts of the half cycle, but the requirement is that when evaluating this equation that the t0 point be moved to the start of the half cycle. It is possible to express the input impedance of the series LCR network as follows. The series impedance is the impedance multiplied by the phasor EJ5, which is the real part of the impedance R, plus the imaginary part, which is the reactance of the two reactive elements. So it will be J omega L minus 1 over omega C. This impedance can be expressed in terms of the real part of the impedance, so the resistance R, and the quality factor and the frequency of the switching signal through the reactive network. The voltage across the resistor is the ratio of the resistance voltage to the reactive voltage in relation to the total input voltage. In other words, mathematically what it actually means is that the output resistance as a function of frequency is the input voltage multiplied by R over R plus the reactive part, and this is actually just a voltage divider equation. It can more simply be written as VI multiplied by the real part of the load divided by the impedance of the load. Using this derived expression for the impedance, the voltage across resistance can be written in terms of the input voltage multiplied by a constant which is determined by the quality factor of the network as well as the frequency of oscillation. It can be seen that if the frequency of oscillation is equal to the resonant frequency, then this term over here will cancel out, since omega 0 over omega 0 is 1, 1 minus 1 is 0, 0 multiplied by Q is 0. So the quality factor of the network doesn't actually matter at the resonant frequency, and thus the voltage over the resistor will be the total input voltage. This is why when looking at the voltage transfer function, regardless of what the value of Q actually is, maximum power will be transferred when the oscillating frequency of the resonant inverter is exactly equal to the resonant frequency. Where the quality factor starts to come into play is when there is a deviation from the resonant frequency. Shown in this diagram is a two-leg converter which has an additional set of switches and diodes which drive the series network. One of the reasons why this would be done is if the Q of the network is not particularly high. What this means is that the capacitor's ability to provide energy to the resistor part of the load is not good enough to maintain voltage during a single half cycle. For this reason, an additional switching network is required to inject energy into the LCR network. A key difference between this 4-device or 4-switch network and the 2-switching network is that the output voltage for this network is twice that of the single-leg network. Shown in this diagram is once again a single-leg inverter, but instead of having a series network, there is now a shunt network. It should be noted that when referring to a shunt network, LCR network for these types of inverters, the shunt aspect is more aligned on the fact that the capacitive and resistive element are in shunt than having the inductive element in shunt as well. An important characteristic of this configuration is that this load resistance is much higher than the reactance of the capacitor and the inductor. As the load resistance increases, the voltage across the capacitor and the load will also increase. This is because the current which is provided to the load is independent of the load and determined by the reactive inductor and the switches. Thus, increasing the load resistance will also increase the amount of power delivered to the load. For this circuit there is a resonant frequency FR, and what happens at FR is that the current phase shift is 0. This resonant frequency is not the same as the fundamental resonance frequency of the network. The ratio of these two frequencies can be expressed as the square root of 1 minus 1 over the quality factor, as long as the quality factor is larger than 1. What this means is that the higher the Q of the network, then these two frequencies will essentially be the same. This relationship is shown here on the voltage transfer function by the dashed line. If the ratio is less than 1, then this network will behave as a capacitive load, and if the ratio is larger than 1, then this network will behave as an inductive load. Once again, the output voltage across the load is determined on how much of the energy is distributed across all the elements in the network. So once again, the output across the resistor So function of frequency is the input voltage across the entire network multiplied by 1 over the square root of 1 plus omega over omega 0 squared squared plus 1 over q squared multiplied by omega over omega 0 squared. Now if q is very large or tends to infinity, so basically if q is larger than 10, then this term over here will be approximately 0 or much smaller than this term, and then the output voltage across the resistor as a function of frequency can be expressed as the input voltage multiplied by 1 divided by 1 minus omega over omega 0 squared. The parallel resonant network can be combined with a series resonant network to generate a series parallel resonant network. In this network there is an additional capacitor in series with the inductive element. One of the reasons why this additional capacitor is introduced is that it improves the efficiency of the resonant inverter. So this can be seen from the voltage transfer function over here, where even for low Qs there is a very narrow or focused transfer of energy around f over f0. Once the switching frequency starts to diverge from the resonant frequency of the entire network, the amount of energy which is transferred to the load drops off dramatically. A disadvantage of this type of topology is that the inverter cannot operate under short and open circuit conditions. In a short circuit condition, then this R over here will be equal to 0 and this will short out capacitor C2. This means that the only limiting elements in the load will be the inductor L and C1. In such a network, the switches T1 and T4 will have a very low on resistance, and this means that in the case of a short at the output, there may be excessive currents which flow through the switches and through this new load. Resonance source inverters are not limited to being voltage sources, they can also be current source inverters. Here are two examples, both making use of a parallel resonant network, one with only one converter leg and one with two converter legs, forming a classical H-bridge structure.